My name is Yanjun. Today I will introduce comparative synthesis, which is a framework that we use to learn near-optimal network designs by Querie. This is a joint work with Zixuan, Chuan, Xiaokang, and Sanjay from Purdue University. Our idea of the comparative synthesis framework is motivated by the traffic engineering problem. Given a network, there are plenty of source and destination pairs. There are multiple paths between each source and destination, and traffics in the network may have different priorities. Also, we need to take capacity and security restrictions into consideration, and given a set of demands, taking all aspects into the consideration, the network architect needs to figure out how to allocate resources to different traffics. This task can be formulated into a synthesis problem. For example, the sketch code on the right-hand side encodes all the hard constraints the network of this network design problem. For example, the topology of the network, every link's capacity is not exceeded, and every flow's demand is satisfied. Given this code, Sketch can find a network allocation in negligible time and returns the result throughput and latency, which are metrics that the network architect cares most in this case. So can we go home? No, because the real challenge is not finding a random solution, but finding the optimal solution from a nearly infinite number of solutions. Each one may yield a different throughput and latency combination. So the problem today's network architects struggle with is what is the optimal solution? A typical approach for solving this network design problem is to formulate an optimization problem with a well-defined objective. The objectives need to be formulated as closed-form mathematical functions. And given the complexity of many network design problems, this may not be an easy job. For example, to trade off multiple objectives, the researchers at Microsoft proposed an algorithm in their COMP13 paper. The algorithm is based on a manually tuned target function, which assigns weights and thresholds to throughput and latency. These knobs are all manually tuned by architects in a try-and-error fashion. And another example could be the bandwidth enforcer proposed by Google. And this is another optimization algorithm used in the field to enforce fairness requirements for flows across different traffic classes. And similarly, this algorithm also expects a user-provided fair share function. We believe that this is not a unique challenge in the field of computer network, but a general problem for quantitative synthesis. Quantitative synthesis has been known as synthesizing an optimal program based on an objective. Similar to the network design scenario, the user or developer is also always be expected to formulate optimal solution, what an optimal solution is. For example, the sketch-based optimal synthesis, quantitative syntax-guided synthesis, quantitative programming by example. These existing techniques all expect a user-provided objective function. They may provide it in the form of a cost function, weighted grammar, or highly tuned ranking function. So there's a gap between the end user and the synthesizer. Writing the objective function is non-trivial for users without expertise. And let's consider the network design problem mentioned in the previous slide. What on user's mind may be a very vague idea that she tried to maximize throughput while minimize the latency. But the synthesizer is expecting a formally defined mathematical function. So a question comes up, can we synthesize network designs without specifying the objectives? We started to consider if programming by example can help in this case. Because writing formal specification may be challenging for network architects, but it should be relatively easy for them to provide several in-pop examples. But given network design scenario, without specifying the objective function, it's actually very hard for them to provide a specific reward for this network design scenario under their implicit objective function. If they can provide such in-pop examples, they must have already know how to formulate this objective function. Then we observe that given a pair of network design scenarios, it's intuitive for them to provide a relative comparison between these two scenarios and rank which one is more acceptable. For example, based on her experience, she may feel that latency of 100 milliseconds is much better than 300. Based on this observation, we propose an interactive synthesis approach called comparative synthesis that solves quantitative synthesis problem without specifying an objective. In this comparative synthesis framework, there is a learner and the teacher. The synthesizer serves as the learner that is learning the objective and also the corresponding optimal program. And the user will serve as the teacher who is teaching the synthesizer. As the user may be willing to only answer a few number of questions, and she may choose to stop at any time, the learner will maintain a running best and present the running best to the user when she chooses to stop. The learner can only ask comparative queries to the teacher, and two types of queries are allowed in this framework right now. The first one is propose. The synthesizer will propose a candidate program to the teacher and ask the teacher if this proposed program is better than the previous running best. The teacher can either approve or decline. If the teacher confirms that this proposed program is strictly better than the previous running best, then we will update the running best. And the other type of query is compare. In this case, the synthesizer will present a pair of programs to the teacher and ask the teacher to state her preferences. She may prefer one of these programs or think these two programs are equally good. Ideally, this kind of interactions can keep going on until we find the one and only target function that satisfies all the user's preferences. However, since finding the perfect target function may be impossible because it may not have a closed form representation, or the user may choose to stop prematurely. So our learner's goal is not to find the perfect objective function, but spending a budgeted number of queries and produce the near optimal program from the perspective of the teacher. Since we are trying to produce a near optimal program, we need to know how close a solution is to the ground truth optimal. But we do not know the target function. So we define a natural notion called quality of solution to estimate the solution quality. The quality of solution is intuitively the relative rank of the solution among all possible solutions. For example, if we order all the solutions from the worst to the best, and if there is a candidate program P1 has the quality being 0.7, then it means that P1 is better than or at least equal to 70% of all possible solutions. Since computing the exact quality can be extremely expensive because we may have infinite number of possible solutions, in our evaluation, we estimate this solution quality by sampling. Here I will show an example run of the comparative synthesis framework. Let's still consider the target function to be an objective function that rewards a higher throughput and lower latency. In the first 3 iterations, the synthesizer keeps proposing new programs to the teacher, and the teacher also confirms that these new programs are better than the previous running best in each iteration. But then in the later 2 iterations, the synthesizer proposed 2 more programs, but they are rejected by the teacher. And then in the 6th iteration, the synthesizer presents a pair of programs to the teacher, and based on the feedback that she prefers one of these programs, in the next iteration, the synthesizer proposes another program to the teacher, and the teacher later confirms that this is the best program so far. So after all these 7 iterations, the quality of solution of P7 already achieved 97%. And if the teacher wishes to answer more queries, the quality of solution can be further improved. Now let's see what's happening under the hood. A key insight behind our algorithm is that neither the programs or the target functions alone is an ideal search space, because many target functions can correspond to the same optimal program, and many programs may not be optimal at all. Therefore, we define a unified search space which we call Pareto candidate set. Intuitively, a Pareto candidate set is a set of target functions and its corresponding distinct optimal programs. Now, every response to a query will prune this search space. Since our goal is to minimize the number of queries, the learner has to pick the most informative query in each iteration such that the size of this candidate set can be reduced as much as possible. We estimate the informativeness of queries by counting how many candidates will be removed from the set at the worst case if a query is asked. Take the compare query, for example. Given a candidate set of size 5, suppose that represents P0 and P1 to the user. And if the user prefers P0, then 4 candidates can be knocked out from the set. But if she prefers P1, then only 1 candidate can be removed. And none of our target functions in the candidate set believe that P0 and P1 are equally good. Take the minimum of all these 3 cases, the informativeness of this query is 1. Suppose the other compare query has informativeness being 2. Since our synthesizer tends to ask queries with higher informativeness, given these 2 queries, the second one will be picked. We have the same idea for picking the queries for propose. Our learning algorithm is then very straightforward. The algorithm starts by sampling a moderate-sized candidate set, and then in each iteration, it picks the most informative query and prunes the search space based on the teacher's responses. When the number of remaining candidates in the set is below a predetermined threshold, the algorithm will regenerate more candidates based on the already collected preferences. The algorithm terminates and returns the current running best when the user chooses to stop, or there's only one program that satisfies users' preferences. As one of the goals of our voting-guided algorithm is to minimize the number of queries, we also prove the convergence rate of this algorithm. In other words, how fast does the output solution approach the optimal? We proved that, in general, the voting-guided algorithm guarantees a logarithmic rate of convergence. The proof idea is also very straightforward. Every query discusses at least one randomly generated candidate. Although the convergence rate is not very fast, but if we plot the guaranteed solution quality for the 10 first iterations, we can see that the solution quality already achieves 90% after the first 6 queries. We also considered if there's any cases where our voting-guided algorithm can converge faster. The answer is yes, when the search space is sortable. Given a set of target functions, and each target function can be mapped to its optimal program, the sortability makes sure that the candidates in the candidate set can be ordered in a way such that every target function with its corresponding program always prefers its near neighbor to the further neighbors. And our running example shows a sortable search space. If we continue improving one of the metrics, in this case, throughput and latency, the benefits of the improvements would be smaller. For instance, increasing the throughput from 1 gigabit per second is more favorable than the improvements from 2 to 3. We have proved that when the target function space is sortable, the algorithm guarantees a linear rate of convergence. And the proof idea is very similar. Every query discusses at least 1/3 of the candidates from the pool. We have prototyped the comparative synthesis framework as a tool called NetNQ, which is an interactive system that produces near optimal network designs by asking 10 queries. We have evaluated NetNQ on 4 real-world network design scenarios and 4 real-world network topologies. The largest topology we considered has 114 nodes and 135 links. The size of this topology is already beyond the ones usually considered in the traffic engineering community. We first conducted the experiments with a perfect oracle. The oracle served as a teacher who answers all the queries correctly based on a ground truth objective function, but the objective function is unknown to NetNQ. As a first-of-its-kind system, we do not have other systems to compare NetNQ with, so we compared full NetNQ with a baseline version which randomly makes queries, but without pruning the search space. The results are shown in the figure. we can see that NetMQ performed constantly better than NetMQ no prune in the every scenario and topology combinations. We also adapted the oracle to simulate imperfect teachers whose responses are potentially inconsistent. We evaluated NetMQ and NetMQ no prune with this imperfect teacher, and we can still see that NetMQ continues to outperform NetMQ no prune. And we also tested NetMQ on different inconsistency level as controlled by a parameter P. And we can see from the figure that NetMQ can still achieve relatively high solution quality with high inconsistency level. To evaluate the effectiveness of NetMQ, we also conducted a small-scale user study involving 17 participants. The primary goal of this user study is to evaluate NetMQ on objectives that is arbitrarily chosen by the user, and even the shape of the objective function is unknown to NetMQ. Also, a real user may provide inconsistent responses. In our user study, most of the participants are computer networking practitioners or researchers with more than 2 years of experience managing network. And most of our participants wish to achieve a higher allocation for a higher priority class while not starving the lower priority classes. However, based on their qualitative comments, we found their policy actually differed greatly. We collected the user feedback on the quality of recommendations produced by NetMQ and also the response time. All of our participants found that the final recommendation produced by NetMQ is consistent or somewhat consistent with their policies. And their qualitative comments are also very encouraging. And NetMQ's response time was also acceptable for a majority of users. We also collected the time taken by NetMQ in each iteration. The time taken by NetMQ was hardly a second, and it is much smaller than the user think time, which varies from 8 to 12 seconds. This indicates that NetMQ can be used interactively. In summary, we presented the first effort at learning the near-optimal network designs through Querie without a given objective function. And we proposed a new formal framework for comparative synthesis through interactions with users. And we also developed an algorithm for the framework that combines program search and objective learning. The goal of this algorithm is to achieve high solution quality with few queries. And we have prototyped the framework, and our experimental results have shown the promise of the framework. That concludes my presentation. Thank you.
Any questions?
Hi, I'm Jocelyn Chen from UT Austin. So a lot of time when you were trying to, there was a metric you were talking about where you prune the program based on how much of the search space it can be pruned by estimating, okay, for this certain target function, how many optimal program are defined by those certain metrics. So I'm wondering a lot of time it's even difficult to have to synthesize all the program that satisfy a certain target function. I'm wondering how you do that. Do you use like an FTA or what's the internal of that part of the synthesis?
So the question was how to synthesize the optimal program for a specific target function?
How do you synthesize a set of optimal program for the target function? Usually, how large is the set?
For the network design problems, actually the search space is infinite because they are all in real value domain. So we were randomly sampling solutions from the space. And our algorithm also started with a moderate-sized candidate set, and we will regenerate the candidates when the size of the candidate set is below some threshold. And for solving the optimization problem, we are using a tool called Groby to do this job. Does that answer your question?
Cool. Yeah. Thank you.
Hi, I'm Eric Campbell from Cornell. Could you speculate on other kinds of synthesis problems where comparative synthesis or voting-guided learning, the voting-guided learning framework could be useful?
Sorry, I may miss the last part of the question.
Could you speculate on where your techniques, comparative synthesis or voted-guided learning, could be useful besides networking?
Yeah, I think I mentioned several quantitative synthesis problems in our field. And we believe that comparative synthesis is not specially designed for network design problems. This should be a general framework that can be applied to all kinds of quantitative synthesis problems. And for example, the quantitative syntax guided synthesis or quantitative programming by example we may apply this framework to them.
Hi, I'm Andrew from Princeton. I was wondering, were you given as input a way to take a sample program to its metrics? And for networking, how did you do that? Was it like a simple packet trace, I guess, in a simulator, or yeah, that's the question.
So the question was, what kind of programs are we present to the user? Is that correct?
No, I was wondering how you compute, like for in your running, you had like the throughput and the latency. How did you compute that from an example program that you had?
Sorry, I still didn't get the question. Can you?
I think the question was, how do you compute the throughput and latency numbers, for example, from a given program?
Yeah, basically, were you given as input a way to compute that, or did you come up with something specifically for your networks for yourself?
Yeah, given a network design scenario, we already have we already know the network constraints, so we can construct a partial program to enforce the hard network constraints, and based on that, we can compute the qualitative synthesis problem is to find the allocations to fill the partial program, and based on the allocations, we can compute the matrix in the network, for example, the throughput, the latency. Does that answer the question?
I'm Faizan Asrobati from CISPA. I'm wondering which kind of security restriction did you synthesize, and how did you do that?
Sorry, can you speak a little bit louder?
I think the question was what kind of security restrictions that you take into consideration when you're synthesizing programs.
Let's see. I think in our evaluation, we do not have any network scenario involving security problems. We do have some. We considered problems such as balancing throughput and latency, or fairness sharing across different traffic classes. Also consider the problems of achieving satisfying network performance in normal cases, and also one single link failure cases, and also consider link utilization and the capacity of the and latency of the network. So to answer your question, we do not consider any security problems.
Okay, let's thank Yanjun again.